It is normal to install surge arresters on feeder load interrupter switches. Surge arresters protect electrical equipment against transient overvoltages, such as lightning strikes and switching surges. By providing a low resistance path to ground, surge arresters divert these high-energy surges away from sensitive equipment. The appropriate surge arrestor class depends on the system voltage and level of protection required. For 34.5 kV feeder load interrupter switches, distribution and station classes are typically used. Distribution class arresters are suitable for systems where low levels of overvoltage protection are needed. These arresters are typically used on distribution lines and customer service drops. Station class arresters are designed for systems with higher levels of overvoltage exposure. These arresters are commonly used at substations and transmission lines. For a 34.5 kV indoor feeder load interrupter switch, it is recommended to use a station class surge arrestor. Station class arresters provide a high level of protection against overvoltages that may occur on transmission or distribution lines, such as lightning strikes and switching surges. The surge arrestor should be installed as close as possible to the load interrupter switch to minimize the distance between the protection device and the equipment being protected. Proper grounding is essential for the effective operation of surge arresters. The ground connection should be low impedance and have sufficient current carrying capacity. Surge arresters should be inspected and tested regularly to ensure their proper operation. Replace any damaged or expired arresters promptly. Let's delve deeper into the selection process for surge arresters, particularly focusing on the distinction between distribution and station class arresters. When choosing a surge arrestor, consider the following factors. Firstly, the system's voltage. Surge arresters are rated for specific voltage levels. Selecting an arrestor with an appropriate voltage rating that matches or slightly exceeds the system's nominal voltage is crucial. Secondly, the anticipated surge current magnitude. This is the maximum current that the arrestor is expected to handle during a surge event. The higher the potential surge current, the more robust the arrestor needs to be. Consider the potential for lightning strikes and switching surges in the specific application. Thirdly, the energy handling capability. Surge arresters dissipate energy during a surge event. The arrestor's energy handling capability must be sufficient to withstand the energy associated with the anticipated surges. This is typically expressed in kilojoules. Fourthly, the protection level. This refers to the maximum voltage that the arrestor will allow to pass through to the protected equipment during a surge. A low protection level provides better protection but may also result in more frequent arrestor operation. Fifthly, the location. Indoor applications generally require different arrestor designs than outdoor applications due to environmental factors. In the case of a 34.5 kV indoor load interrupter switchgear, the environment is typically controlled, reducing the risk of contamination. However, proper ventilation and temperature control should be ensured to prevent overheating of the surge arrestor. Distribution class arresters are typically metal oxide varistor, MOV, based arresters that provide adequate protection for distribution systems. They are designed to handle lower surge currents and energy levels compared to station class arresters. Their clamping voltage, which is the voltage at which the arrestor starts to conduct, is generally higher than that of station class arresters. Distribution class arresters are a cost-effective solution for protecting equipment in distribution systems where the risk of severe overvoltages is relatively low. They are often used in applications such as protecting transformers, cables, and other equipment connected to distribution lines. Station class arresters are designed for more demanding applications where higher levels of overvoltage protection are required. They typically utilize more robust MOV blocks or other advanced technologies to handle higher surge currents and energy levels. Station class arresters have a lower clamping voltage than distribution class arresters, providing better protection for sensitive equipment. They are commonly used in substations, transmission lines, and other critical infrastructure where the consequences of equipment failure are significant. Considering the factors above, a station class arrestor is generally recommended for 34.5 kV indoor feeder load interrupter switchgear. This recommendation is based on the need for a higher level of overvoltage protection due to the potential for lightning strikes and switching surges on transmission or distribution lines. The station class arrestors' lower clamping voltage and higher energy handling capability provide a greater margin of safety for the protected equipment. In addition to selecting the appropriate surge arrestor class, proper installation and maintenance are essential for ensuring its effective operation. Here are some key considerations. Firstly, the location. Install the surge arrestor as close as possible to the equipment being protected, in this case, the load interrupter switch. This minimizes the length of the connecting leads, reducing the inductance and improving the arrestor's ability to divert surge currents. Secondly, the grounding. Provide a low-impedance ground connection for the surge arrestor. The ground conductor should be as short and straight as possible to minimize inductance. Connect the ground conductor to a dedicated ground bus or ground cord that is properly bonded to the equipment grounding system. Thirdly, the coordination. Coordinate the surge arrestor with other protective devices in the system, such as fuses and circuit breakers. Ensure that the arrestor operates before other protective devices to prevent damage to the protected equipment. Fourthly, the inspection. Regularly inspect the surge arrestor for any signs of damage or deterioration, such as cracks, corrosion, or discoloration. Use appropriate testing methods to verify the arrestor's performance and ensure that it is operating within its specifications. Fifthly, the replacement. Replace any surge arrestors that are damaged, deteriorated, or have reached the end of their service life. Follow the manufacturer's recommendations for replacement intervals and procedures. Furthermore, consider the specific characteristics of the load interrupter switchgear when selecting and installing surge arrestors. Load interrupter switches are designed to interrupt load currents, but they may also be subjected to switching surges during operation. These switching surges can stress the insulation of the switchgear and other connected equipment. Therefore, it is important to select surge arrestors that can effectively mitigate these switching surges. The surge arrestor should have a low enough clamping voltage to protect the switchgear insulation from overstress, but it should also be able to withstand the repetitive switching surges without premature failure. The surge arrestor's energy handling capability should be sufficient to dissipate the energy associated with the switching surges. The surge arrestor should be properly coordinated with the load interrupter switch to ensure that it operates correctly during switching operations. This may involve adjusting the arrestor's voltage rating or adding additional protective devices, such as surge capacitors. In addition to protecting the load interrupter switchgear, surge arrestors can also protect other equipment connected to the feeder, such as transformers, cables, and motors. By diverting surge currents away from these devices, surge arrestors can prevent insulation breakdown, equipment damage, and service interruptions. When selecting surge arrestors for feeder protection, consider the characteristics of the connected equipment, such as its insulation level, surge impedance, and susceptibility to overvoltages. The surge arrestors should be sized and located to provide adequate protection for all of the connected equipment. It is also important to coordinate the surge arrestor with other protective devices in the system to ensure that they work together to protect the equipment from overvoltages. In summary, the selection and installation of surge arrestors for 34.5 kV indoor feeder load interrupter switchgear requires careful consideration of several factors, including the system voltage, anticipated surge current magnitude, energy handling capability, protection level, location, and the characteristics of the connected equipment. A station class arrestor is generally recommended for this application due to the need for a higher level of overvoltage protection. Proper installation, grounding, coordination, inspection, and maintenance are essential for ensuring the effective operation of the surge arrestors. By following these guidelines, you can protect your electrical equipment from transient overvoltages and ensure the reliable operation of your power system. Let's expand on the importance of proper grounding for surge arrestors. A surge arrestor's effectiveness hinges critically on a low-impedance ground connection. Think of it like this: during a surge event, the arrestor provides a path for the high-energy surge current to flow to ground, safely diverting it away from the protected equipment. However, if the ground connection has high impedance, it's like putting a roadblock in the surge's path. This impedance restricts the flow of surge current, causing the voltage at the arrestor to rise. This elevated voltage can defeat the purpose of the arrestor, potentially exceeding the insulation withstand capability of the protected equipment and causing damage. To achieve a low impedance ground connection, several factors must be considered. Firstly, the length of the ground conductor. The ground conductor should be as short as possible. Longer conductors have higher inductance, which increases impedance, especially at the high frequencies associated with surge currents. Secondly, the conductor material and size. Use a conductor with sufficient cross-sectional area to handle the anticipated surge current. Copper or aluminum conductors are commonly used. Refer to relevant standards like the National Electrical Code, NEC, to determine the appropriate conductor size based on the system's fault current. Thirdly, the bonding. Ensure that all ground connections are properly bonded. Bonding involves creating a low impedance connection between different metallic parts of the grounding system. This helps to equalize the potential between these parts and prevent circulating currents. Fourthly, the ground grid. In many substations and industrial facilities, a ground grid is used to provide a low impedance ground reference. The ground grid consists of a network of interconnected conductors buried in the earth. The surge arrestor should be connected to the ground grid at a point that is as close as possible to the equipment being protected. Fifthly, the soil resistivity. The soil resistivity affects the overall impedance of the grounding system. In areas with high soil resistivity, it may be necessary to use ground enhancement techniques such as adding chemical treatments to the soil or installing ground rods to reduce the impedance. The NEC provides guidelines for grounding and bonding electrical systems, including surge arrestors. Table 250.166 specifies the minimum size of grounding electrode conductors for alternating current systems. Section 250.50 covers grounding electrode systems, while Section 250.92 discusses bonding of equipment grounding conductors. It is crucial to adhere to these NEC requirements to ensure a safe and effective grounding system. Another critical aspect to consider is the coordination of surge arrestors with other protective devices in the system. Surge arrestors are not the only protective devices in an electrical system. Fuses, circuit breakers, and other protective devices are also used to protect equipment from overcurrents and overvoltages. To ensure that all of these devices work together effectively, they must be properly coordinated. Coordination involves selecting the appropriate ratings and settings for each protective device so that they operate in the correct sequence during a fault or surge event. The goal is to ensure that the device closest to the fault or surge operates first, isolating the affected portion of the system while minimizing the impact on the rest of the system. For surge arrestors, coordination involves selecting an arrestor with a voltage rating and clamping voltage that are compatible with the insulation withstand capability of the protected equipment. The arrestor should operate before other protective devices, such as fuses or circuit breakers, to prevent damage to the equipment. The arrestor's energy handling capability should be sufficient to dissipate the energy associated with the anticipated surges without causing it to fail prematurely. Coordination studies are often performed to determine the optimal settings for protective devices in an electrical system. These studies involve analyzing the system's impedance, fault current levels, and the characteristics of the protective devices. The results of the coordination study are used to select the appropriate ratings and settings for each device, ensuring that they operate in a coordinated manner. In addition to the technical aspects of surge arrestor selection, installation, grounding, and coordination, it is also important to consider the economic factors. Surge arrestors represent an investment in protecting electrical equipment from damage due to overvoltages. While the initial cost of surge arrestors may seem significant, it is important to weigh this cost against the potential cost of equipment damage, downtime, and lost production due to overvoltage events. A cost-benefit analysis can help to determine the optimal level of surge protection for a particular application. This analysis should consider the probability of overvoltage events, the potential cost of equipment damage, the cost of downtime, and the cost of surge protection equipment. In some cases, it may be cost-effective to install surge arresters on all critical equipment, while in other cases, it may be more cost-effective to focus on protecting only the most sensitive or critical equipment. Another economic factor to consider is the life cycle cost of surge arresters. Surge arresters have a finite lifespan and must be replaced periodically. The replacement interval depends on the arrestor's design, the operating conditions, and the frequency and severity of surge events. When evaluating the cost of surge arresters, it is important to consider the cost of replacement, as well as the cost of maintenance and inspection. In addition to the technical and economic factors, it is also important to consider the regulatory requirements related to surge protection. Many countries and regions have regulations that require surge protection for certain types of electrical equipment or installations. These regulations are designed to protect people and property from the hazards of overvoltages. It is important to be aware of the regulatory requirements that apply to your specific application and to ensure that your surge protection system complies with these requirements. The NEC, for example, provides requirements for surge protection in various sections, including Article 280, which covers surge arresters, and Article 285, which covers surge protective devices. Compliance with these requirements is essential for ensuring the safety and reliability of your electrical system. Finally, it is important to stay up to date on the latest advancements in surge arrestor technology. Surge arrestor technology is constantly evolving, with new materials, designs, and features being developed to improve performance and reliability. By staying informed about these advancements, you can ensure that you are using the best available surge protection technology for your application. Some of the recent advancements in surge arrestor technology include the development of metal oxide foresters, MOV, with improved energy handling capability, the use of advanced insulation materials to improve arrestor reliability, and the integration of surge arresters with monitoring and diagnostic systems. These advancements can help to improve the performance and reliability of surge protection systems and reduce the risk of equipment damage due to overvoltages. In conclusion, the selection and installation of surge arresters for 34.5 kV indoor feeder load interrupter switchgear requires careful consideration of several factors, including the system voltage, anticipated surge current magnitude, energy handling capability, protection level, location, grounding, coordination, economic factors, regulatory requirements, and the latest advancements in surge arrestor technology. By following these guidelines, you can protect your electrical equipment from transient overvoltages and ensure the reliable operation of your power system.